Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College in Silicon Valley, and it's my pleasure to welcome all of you in the Smithwick Theater and everyone listening and viewing us from home to this, the first lecture in the 16th annual Silicon Valley Astronomy Lecture Series. This public outreach series is co-sponsored by 4 different organizations: NASA's Ames Research Center, the Astronomical Society of the Pacific, the SETI, or Search for Extraterrestrial Intelligence Institute, and the Foothill College Astronomy Department. And we're grateful for all of them for their support. This is a series of free public lectures taking place in Los Altos Hills 6 times a year, bringing some of the most distinguished astronomers in our region and in the country to tell us about what's new and sexy in astronomy. Tonight's speaker, one of my very favorites in astronomy, is Dr. Carolyn Porco. She is the imaging team leader for the Cassini mission, which is right now circling Saturn and bringing us tremendous pictures and information about Saturn, its moons, and its rings, and that's what you'll hear about tonight. She's also a visiting scholar here at the University of California at Berkeley. Dr. Porco was an imaging scientist for the Voyager mission in the 1980s and is also part of the imaging team for the New Horizons mission at Pluto. Her specialty is the study of planetary rings and their interactions with the same planet's moons. And also she specializes in the geysers on Saturn's intriguing little moon, Enceladus. She appears frequently on national television news and in documentaries, and she was a character consultant on the movie Contact, that I think many of you know and love. In 2000, she was also a consultant for the 2009 Star Trek movie. And you can see some of her fabulous Saturn pictures in that 2009 Star Trek movie. In 2010, Dr. Porco was awarded the Carl Sagan Medal of the American Astronomical Society for excellence in the communication of science to the public. And in 2012, Time magazine named her one of the 25 most influential people in space. So, ladies and gentlemen, it's both a personal pleasure and a professional privilege to be able to present to you Dr. Carolyn Porco.
Can you hear me? Yes, you can. Whoa. So, well, thank you, Andrew, for that lovely introduction and for inviting me here. Andrew has been trying to get me to come speak here, I think, for 16 years. And it took me to move here to actually make it happen. But anyway, thank you very much. So I'm very happy to be here. And I'm going to begin with a story tonight. And it's a tale about the inhabitants of a small, rocky, ocean-covered little world in orbit around an ordinary star, one of hundreds of billions of stars in an ordinary galaxy. As the tale is told, these beings, refusing to accept limitations, laughing at the idea of boundaries, and with unbridled imagination, over time created the languages of mathematics and science. And they became skilled technologists. They developed mastery over gravity, and eventually they flung themselves and their machines off their home planet and deep into the space surrounding their sun. And they did this merely in response to an innate desire to explore and to learn something about their cosmic neighborhood. But they did this also to seek the answers to questions that had vexed them and every generation of their ancestors before them. How is it that their small planet and they living on it came to be? And what was the great cosmic theater in which life on their planet had unfolded? Well, of course, you know, this is a story about us. And we, Homo sapiens, have been interplanetary travelers now for well over 50 years. And in that time, we have been to every corner of the solar system. We have dispatched our robotic spacecraft to all the planets, all 8 of them. We have landed on comets and asteroids. We have finally, historically, triumphantly sent our craft past into the far reaches of the sun's influence, into that realm of debris called the Kuiper Belt, to pay visit to its most famous member, Pluto. And in what I regard as humanity's finest hour, we even set foot on our own moon. And these epic voyages have indeed rewarded us with insights into the origin of the Earth and its sibling planets, and they have shown us with remarkable clarity just exactly what our cosmic place really is. And it's a fabulous story when you think about it. Part extreme exploration, certainly part scientific discovery, but also part search for meaning, the meaning of our existence. And a major chapter in this story, one that's been ongoing now for 25 years, began when a mission named Cassini was started, and from its conception, it was meant to be a joint venture between the United States and Europe, and it called for nothing short of a complete, comprehensive, in-depth examination of everything in the Saturnian planetary system. The planet, its magnetic field, its enormous set of rings, and of course, its collection of many, many moons. And we have been now in orbit around Saturn we're in our 12th year, and there's no way that I can tell you everything that we have found in that time, or show you all the beautiful scenery and vistas that we have come to see. So I'm just going to show you some of the highlights, and I think these are the highlights that convey just how profoundly successful this mission has been. And then I will leave with some thoughts about what I think will be Cassini's legacy once it is finally over. So Saturn is very far away. And Cassini at launch was very big and very heavy. It's the size of a school bus, and it weighed nearly 6 metric tons. And taking all of that and putting it on the largest, most powerful stack we could construct, Titan IV missile, solid rocket motor strap-on, Centaur upper stage, all of that wasn't enough, didn't have enough oomph to get it to Saturn directly. So we had to loop it around the inner solar system twice. It took 2 years. Passed it by Venus twice and the Earth once. This is all for gravity assistance to give it more speed. In a terribly poetic coincidence on the eve of the year 2001, and if you're my age, you know what that means. We passed it by the planet Jupiter for the final push to Saturn, where it arrived in early July 1, 2004. Now, you have to keep in mind that the object of the exercise is to get the spacecraft to its target as quickly as possible, so that those of us who were involved in the mission are still alive by the time the spacecraft gets there. And that means that by the time it gets there, it's screaming by, and we actually have to slow it down. In fact, what we do is we slow down its acceleration to allow it to be caught into orbit around Saturn. And that's what happened on July 1, 2004, and it is depicted in this artist's rendition here. This is the Saturn orbit insertion maneuver. The fuel, half the mass of the spacecraft at launch was fuel that was expended in this maneuver. For 90 minutes, it slowed the spacecraft down, and then we were finally in orbit. And once in orbit, the tour around Saturn began, and this is what the initial 4 years look like. Variable orbits, and the purpose of that, of course, is because there's a lot to see in the Saturn system. We want to be near the moons. We want to be in the equator plane so we can look at the equatorial and mid-latitude regions of the planet and the moons, but we also want to crank up the orbit so that we can look at the polar regions, and of course, we can look down on the rings. And so this is how it was done. Titan is the moon that is used as the gravity assist body in the Cassini tour. So Saturn, of course, was one of our main objectives, that is to study the planet itself, to understand in particular its meteorology, and we've been doing a lot of that over the last 11 years. We have a very good grasp now of the wind speeds throughout the atmosphere. We've been able to study the role of eddies in powering those winds. We have watched the life cycle of small-scale storms, and on it goes. But it was a remarkable thing that we were there in December 2010 and January and onwards 2011 to witness the development of a storm that on Saturn only appears once every 20 or 30 years. And here you're seeing it in full development. It developed in the northern hemisphere, first as just a little convective spot, and then it grew over the course of just 2 months. It ended up wrapping itself all the way around the planet, and it was like lightning strikes, 10 times those of normal Saturnian storms, and lots of radio waves, thundering basically. And we still don't know. I should say this, it was obviously, maybe it's not obvious, it was the largest storm that we've ever been able to observe from a spacecraft. So it was really just an unprecedented opportunity to study the mechanisms responsible for this. And it went on hissing at us. It went on hissing for nearly 2/3 of a year. So the largest and the longest lasting storm we've ever had the opportunity to witness. The atmospheric scientists on my team and also throughout the Cassini project are going to be spending a lot of time trying to figure out what makes these storms work. We're not exactly sure at the moment. We arrived at the height of southern summer. Here you could see it is northern spring because the shadows are in the southern hemisphere. And with northern spring, it started to reveal things in the northern hemisphere and around the pole, the North Pole of Saturn, and we came to see something we had discovered with Voyager that was called the hexagon. This is a feature that is 2 Earths across. There are wind speeds that blow here, some 220 miles per hour. And I have to say, whenever we put anything on our website having to do with the hexagon, the hits go through the roof. People just can't get their head around things with straight sides in an atmosphere, and they think this is, I don't know, some kind of crystal energy. I don't really know. But really, it is nothing more than a very stable, very continuous jet stream with 6 waves in it. And it looks like it's straight-sided just because it's wrapped around a sphere, but it really is, in that regard, no different than the Earth's jet stream. And here is a video I pulled off the Goddard Space Flight Center website showing real data on the Earth's north polar jet stream. And you can see it also has about 6 or 7 waves in it, but it's very discontinuous, it's very variable. That's because systems on the Earth, atmospheric systems, run across hill and dale and ocean and forests and so on, all these things that inject friction into them and run them down, and then they have to get started again, and they become variable and discontinuous and so on. None of that happens in the giant planets. It doesn't happen on Jupiter, it doesn't happen on Saturn, Uranus, or Neptune. And so in those systems, in those planets, atmospheric systems can last a very long time and be very stable. And that's all the hexagon really is. So my apologies to the New Age people, but you can quit praying to it. And surely one of the most beautiful images that we in my shops, my Cyclops back in Boulder, where we process most of the images that we release to the public, one of the most spectacular ones is this. And it was so beautiful, it was considered so beautiful and made it all the way to the nightly news. Brian Williams talked it up. This is the center of the hexagon. It's a vortex right at the North Pole of Saturn. It has an eye wall. The winds blow here some 330 miles per hour. That's 50% greater than the winds that leveled Moore, Oklahoma, some years back. So it's like a hurricane or a tornado, except it's very big. It's as big across as half the US. And again, here's another feature that will get a lot of attention over the years, trying to understand its origins and what is going on in it. But these are the kinds of things that we have been discovering on Saturn with Cassini. On Earth, one of the loveliest sights that we could see are the shifting aurora, and we've seen them too also on Saturn. Here we are, of course, in orbit around Saturn, so we're traveling with Saturn, but Saturn is moving through space. So over the 10 hours of this movie, you see the stars go passing by, but you can see ripples in the curtain of auroral emissions, looking rather spooky and also looking rather lovely, at least to us. The rings, of course, are what make Saturn the icon among planets that they are. They are a tremendous visual spectacle. They are 280,000 kilometers across. They would fit in nicely between the Earth and the Moon, just one into the other. And they consist of countless colliding bodies composed of water ice, ranging in size from small houses or small apartment buildings, actually, all the way down to the finest talcum powder, screaming around Saturn at 20 to 40,000 miles per hour, but only very gently jostling one another, millimeters per second. And we call this, physicists call this, a very equilibrated system. Any violent collisions in this system died down a long time ago, which is why now they behave the way they do. And for that reason, they are paper thin in comparison. Here's a beautiful picture of Saturn that we took soon after getting into orbit. You can tell it's southern summer because these are the shadows of the rings cast on the northern hemisphere. And you can see this is the ring system. Collapsed down. They are only 1 or 2 stories thick in a modern day building, very, very thin. They trace out the plane of equilibrium around the planet. And bear in mind, if you took all the mass in Saturn's rings and recomposed it into a satellite of the proper density for the Saturn system, it would be no bigger than this little moon here, which is the moon Enceladus. So tremendous visual spectacle for actually comparatively little mass. Now the rings exhibit, despite their meager mass, they exhibit an enormous variety of structures. This was a picture that we took on approach to Saturn. We made sure we took lots of data on approach to Saturn just in case we didn't get into orbit. We'd at least have something to show for all our troubles. And this is a natural color picture showing you the A, the B, and the C rings. You guys come to astronomy lectures all the time, so you know that astronomers have no imagination whatsoever when it comes to naming things. But these are the 3 main ring elements. There's lots of different structures throughout. Each ring is characterized differently, different types of structure in each major ring element. We don't know if that's because they have they're different ages, and so we're looking at an evolution of structure and we're catching them at different times, or is because they have different masses, which they do, very different masses, so we see different types of structures in different rings of different mass. I favor the one I just said, the latter one. This is the most massive ring, the B ring. We see structures, really chaotic looking structures in the B ring. We're starting to get a grasp as to what causes all of this. A lot of the structures, especially those in the A ring, you can't see it too well on this picture, we'll see others where you can, are those types of structures that are created with in resonant interactions between rings and moons. That can create gaps, it can create waves, it can create all sorts of things depending on how big the satellite is. For instance, the outer edge of the A ring is anchored by a resonance with a moon, actually 2 moons, they're called the co-orbitals. And the outer edge of the B ring is anchored by the strongest resonance in the rings, that's the 2-to-1 resonance with Mimas. The ring particles in the B ring go around twice for every once that Mimas goes around. That's the kind of resonant condition that gives you coherent forcing on ring particles that can build up over time and actually do things like bound a ring and prevent it from spreading, which is what is happening at the outer edge of the B ring. Lots of externally caused features, but some of the most dramatic features we've seen are those that are created by moons embedded in the rings. So I want you to pay attention to this little gap here. I don't know if you could see it, right at the edge of the A ring. It's called the Keeler gap. Okay, and in the Keeler gap, we found, with Cassini, we found this little moon. And this little moon is creating waves on the edges of its gap. Okay, this is not too hard to understand. It's what it does is it induces eccentricities into ring particles that normally are in pretty much circular orbits. And because the particles are streaming by them and each one gets a kick, they can all be in phase. And so you get these beautiful waves on the edge of it. All these features, these other features, are the ones that I described to you before. They are there because of gravitational perturbations by orbiting moons that are external to the rings. So we can study this kind of interaction between a satellite and moon, and it really speaks volumes about what is going on, the kind of basically mathematical relationships that are describing or can be used to describe these kind of interactions. And they also can be applied to other disk systems throughout the cosmos. You can see similar things, of course not nearly at this level of detail, but you can see similar things like the opening up of gaps. If a moon is big enough, you could see this in protostellar disks that are being discovered throughout the Milky Way now, and we see similar things happening, at least the generation of spiral waves. So features like this are at the heart of what makes the spiral structure in galaxies. So there's lots of things that we can learn, but we were immensely fortunate and very eager to take advantage of a unique, rare, celestial phenomenon that occurred when Cassini was there. And this was the arrival of spring in the northern hemisphere. This is when, seen from Saturn, the sun, over time, the seasons change, and the sun passes overhead at the equator and then into the north, and we have the arrival of northern spring. And the moment that the sun is shining above the equator, it's shining edge on to the rings. And that means it's lights out on the rings. The rings go dark. And we were very eager to make sure that we collected information during this event, which happened in August 2009, because we knew that with the angle, the shallow angle of the sun's rays on the ring plane, we would be able to see any features, anything that protruded above or below the rings, because it would cast a shadow and it would betray its own presence. The shadow would betray the presence of things that were sticking up, things that you can't see when the sun is high on the rings. And so that's what happened. Here is a mosaic that we took, a mosaic of images we deliberately took to capture this moment. We've had to process it like crazy in order to see the rings. We had to darken the rings by a factor of 60 so that you could see them. And the only illumination really is the illumination from Saturn. That's why it looks the way it does. Sunlight comes, strikes the globe of Saturn, it reflects back onto the rings, and that's why you can see them. But anyway, oops. So what I meant to say is this was an incredible opportunity. We found so many magnificent things we didn't anticipate, simply because we basically saw the rings pop into the third dimension. It was really, it was moving, I have to say. And look at what we saw in the Keeler gap and Daphnis. Here is Daphnis. It's casting a shadow, and remember those waves? Well, it turns out those waves are mountainous rubble piles that reach 2 miles high above the rings. Why is that? It's because we have found that Daphnis is on an inclined orbit, and it makes an excursion 8 kilometers above and then 8 kilometers below, and then 8 kilometers above again, continuously as it orbits. And in reaching out of the, in leaving the ring plane in its orbit, it is gravitationally pulling ring material to follow along with it, and it creates these repeated mountain peaks of rubble. So this was just a beautiful thing to see. But we saw a lot of other things also. Here are the rings. This is the F ring. I'm not going to say anything about that, unfortunately. We don't have time. Here's the outer edge of the A ring. The Keeler gap is not this thing here, actually. The Keeler gap is right in there, so it gives you a sense of scale. Keeler gap is 42 kilometers across. These features here, and this big one here, these are bending waves. Again, they're caused by external moons that are inclined and creating a wave in the ring that looks basically like the wave that you would get if you dropped a pebble on a pond. Okay, the whole entire ring plane, which is only about 30 feet thick, is warped like corrugated cardboard, and so it creates shadows. But the thing, and all of these other things are density waves, but they too have, we find by looking at pictures like this, they have vertical thickness to them. So it tells us something about the way the ring particles are being shoved together in these waves, so much that they end up having to be forced upwards. But the thing I really want to point out to you is this little guy here, sitting outside what is called the Encke gap, another gap that's created by another moon. So let's go zoom in on him. And this turns out to be a feature. We call them propeller features just because we need to give them a name. And they look kind of like propellers. And they are created by, at the center of these features is a moonlet, only in this particular one, only 400 meters across. So about a half a kilometer across. And it is agitating the ring material around it in such a way to create the wings that form this propeller. And we have seen dozens of these in the A-ring, which is where we are now. And we have, from that, inferred the presence of millions of them. And we've even been able to see the largest ones drift as they orbit the planet. They drift back and forward across the rings, mimicking the migratory motions that we believe the planets, as they were growing in the protosolar nebula, underwent. And so this is just one example of the ways in which we have been able to use what we have found with Cassini and Saturn's rings. This is one example of a process that we believe occurred in disk systems, as I said, throughout the cosmos, in forming solar systems that are forming today. There are planets that are forming, and they are drifting backwards and forwards in the same way that these moonlets are drifting backwards and forwards. So it's a touchstone. The rings we knew were going to provide for us a touchstone to other systems of vastly different scales throughout the universe, and that's, of course, one of the reasons why we went to Saturn. Speaking of satellites, the skies of Saturn is accompanied by, oh, I forgot to mention this. This is the outer edge of the B ring. Remember I said that was the place where was the site of the strongest resonance in the rings. And look what we see here. We see lots of peaks. These two are several kilometers up in the, shooting up in the air. As far as we've been able to make out, this was an idea of mine. It's the best anyone's offered so far. Just basing on what we found in the A-ring, with that we know there are lots of moonlets in the A-ring, my suspicion is that we are seeing the presence of moonlets that have gotten stuck in the resonance that's at the outer edge of the ring, caused by the satellite Mimas. And as the ring material streams by these moonlets, it's forced upwards because this is a very densely packed region, and it creates this this forest of peaks, the shadows of which you see here. So I just love thinking of what it would be like to be in a shuttlecraft, flying low across the rings. The rings are only 30 feet thick, but they'd be gleaming white to you, assuming the sun was above you. And it would look to you like this sheet of debris was stretching to infinity, it would be so large. And you're flying along, and you're flying along, and you come upon a wall of rubble 2 miles high. Okay, so I think that needs to go in a movie. And And a good friend of mine who's a space artist did the next best thing, and he put it on canvas. And I'm hoping that someday we actually get to do this. Anyway, so now to satellites. Saturn is accompanied by, I'm losing track, something over 60 moons now. And they fall into two groups. There's the outer group, which is somewhere between 10 and 20 million kilometers distant from Saturn. It is the home of these satellites we call the irregular satellites. They tend to be small. They have very irregular orbits, which is why they're called that. Some of them are prograde, some of them are retrograde, some of them are on very inclined orbits. We believe those are captured from heliocentric orbit. But the ones that have been really studied by Cassini are the inner group. They reach out to something like 3 to 4 million kilometers from Saturn. And insofar as they all orbit in the same plane, they all pretty much are made of the same material, and they were formed at the same time, they are like a miniature solar system. So our goals in studying the Saturn system, the Saturn satellite system, were not only to do a survey and see if we could find any new moons, ones that could not be seen from Earth, not only to come away with an accounting of all their shapes and sizes and compositions and masses and densities and so on, just really do a survey of their physical characteristics. Our goals were not only to understand their geological histories, but also to test our ideas about, use them as a test bed for our ideas about the formation of solar systems, both our own and those that we see throughout the galaxy today. And so we have been doing that for the last 11 years. We've had many very close satellite flybys. We've conducted well over 100 close satellite flybys so far, thanks to that wonderful, unprecedented orbital tour that the mission designers at JPL have designed for us. And we've discovered a great many things about these moons. I can't say everything that we've found about them, but we have returned some spectacular pictures, and I can quickly show you those. Keep in mind, you probably know this already, if you're familiar with astronomy, the moon, our moon, is about 3,500 kilometers in diameter. That's about 60% the size of the US. All the moons of Saturn are smaller than our moon, with the exception of one. So here we go. This is a picture taken soon after we arrived, so you know it's southern summer. These are the shadows in the northern hemisphere of Saturn. And this is the moon Dione, about 1,100 kilometers across, about a third the size of our moon. And this is Dione relatively up close. You can see the bright, icy ramparts of this crater. The satellites of Saturn are largely water ice. They're outsides of water ice. I love satellites like this, especially ones taken near the terminator. This is the moon Hyperion. It's 250 kilometers across, so that's about a quarter the size of Dione, so about a 12th the size of our moon. This is looking like something taken out of the ocean. It looks like a big sponge. We know why it got this way. I don't really have the time to go into it in detail, but it has to do with very low porosity of this moon and low gravity, so that when impactors hit it, any material is just lost and doesn't come back and coat the moon. That's part of the story, but really just a beautiful object. Here is one of the pictures we took early on that really floored everybody. It's just a beautiful picture taken looking up at the edge of the ring. So here's the F ring, this is the outer edge of the rings, but behind that is the shadow-draped blue northern hemisphere of Saturn, and this is the moon Mimas. Here again is Mimas. This is our Death Star. We know that the impactor that created Herschel crater here came that close to smashing Mimas to bits, and so it doesn't take a rocket scientist to suspect that maybe there were moons in the Saturn system that did get smashed to bits, and that's one of the cardinal ideas for how Saturn's rings came about and other planetary rings. Here are just some gorgeous pictures of Titan, which is Saturn's largest moons and one of the standouts in the Saturn system. This is, you could see, it's northern spring because the shadows are in the south. This is Titan seen against Saturn. This is a picture. I love the black and white pictures. They're very moving to me. They look like abstract art. This looks like something that the Russian artist Kandinsky might have painted. Here again is a black and white with Titan, and I think that's Rhea. I don't even know. That's probably Pandora, Prometheus, and Saturn's rings. So the two standouts, of course, of Titan, which is 50% larger than our own moon, is Saturn's largest moon, and until Cassini got there, was the largest single expanse of unexplored terrain that we had remaining in our solar system. And the other standout is this little moon called Enceladus. Now, we knew quite a lot about Titan before we got there with Cassini. We knew from Voyager, we knew that its atmosphere was similar to the Earth's in some regards. It's largely molecular nitrogen, like our atmosphere here. Its surface pressure is actually 50% greater than ours here, so it's a substantial atmosphere. We knew that it had a thermal structure like ours. It has a troposphere where the temperature gets colder with height, and then it has a stratosphere where it gets hotter, and then it gets colder again, and so on, very similar to the Earth's. But it was different in some very fundamental ways. It was suffused with organic compounds. We knew this years ago. And it had no oxygen. And the compounds that were in its atmosphere, things like methane and propane and ethane, some of them, just through theoretical calculations, it was deduced that some of those could be liquid at the surface of Titan. In fact, what methane does on Titan is what water does on the Earth. It could be present as a liquid, a gas, or a solid. So this opened up, literally, a world of possibilities. You could have fine, slow methane rains, big droplets, because they could grow, they'd fall slowly, they have a chance to get bigger and bigger as they fall. They could fall out of the sky and carve gullies and canyons and form cataracts and rivers and so on, and wash any sludge that had come out of the atmosphere, any of the haze particles that we see in Titan. And I guess I neglected to mention it's 200 kilometers worth of globe enshrouding haze on Titan that makes high noon on Titan as dark as deep Earth twilight. It was believed that those haze particles could fall down through the atmosphere. They could grow with time and fall, cover the surface in a sludge. You could have methane rains falling and washing the sludge off the high mountain peaks through canyons and gullies and into low-lying depressions and basins and so on. And so we did, because of these impressions that we had about what the surface of Titan and the environment of Titan's surface would be like, we had this very distinct impression that when we got there with Cassini, we would find the surface was covered with liquid hydrocarbons. I mean, this was the body fantastic for us on Cassini. What would the surface of Titan look like? We were expecting bodies of liquid hydrocarbons. And so just imagine what we were thinking. You know, you're standing on the surface of the moon in the outer solar system, and it's dark, it's eerie, it's misty, it's 300 degrees below 0 Fahrenheit, it's cold. Of course, you are properly attired. And you are standing on the shores of Lake Michigan brimming with paint thinner. I mean, that's the kind of impression that we had in going to Titan. It was really, I mean, you know, one of the most fabulous things about being in this business is the intense feeling of being an explorer that it gives you. And when it came to wondering what we were going to find on Titan, it's goosebump raising. It was beautiful. So anyway, for all of these reasons, Cassini was deliberately equipped to the gills with instruments that could get to see down to the surface of Titan, something we couldn't do on Voyager. It did not have the proper equipment. But we learned from our mistakes on Voyager, and we equipped Cassini to see down to the surface. And one instrument that Cassini carried that has been singularly successful has been the radar instrument. It's an instrument that's like the radar instrument that mapped the surface of Venus in the early 1990s. It has no trouble seeing through the haze or thick atmosphere. It works with microwaves that shower the surface, and then your antenna on your spacecraft collects the radiation that is reflected from the surface, and those signals are constructed back down on the ground on Earth to form a two-dimensional image. Well, Cassini had one of those, and then, of course, there was the Huygens probe, the deployment of which occurred 6 months after Cassini got into orbit, and this was a flying saucer-shaped device built and operated by the Europeans and carried by Cassini to Saturn that drifted down on a piece of fabric, if you will, for 2.5 hours through the Titan atmosphere and came to rest on the equatorial plains of the moon. And it was it was historic. It was landfall in the outer solar system, and it took many measurements of the atmosphere on its way down, measuring pressure and temperature, atmospheric transparency, and it had cameras aboard that could take pictures of the scene, and it deliberately spun as it fell so that these cameras could just sweep along and make pictures as they fell. And it's hard to describe what it was like to see the pictures that the probe had taken of the surface. Of course, we weren't sure the whole thing would be successful, so it was just a remarkable moment, but this is what they were like. They were everything our pictures from orbit were not. Our pictures from orbit were blurry, hard to make out. I mean, we did get to see the surface, but it was very blurry. There's no shadows on the surface because it's got a thick cloud cover, if you will. So the technique that planetary scientists have used for all these 50 years in examining and interpreting spacecraft data, the technique of knowing where the sun is, and this is on an airless body, and you could see the length of a shadow, you could deduce how high or how low something is. That didn't work on Titan. So we had very little information from orbit, but the Huygens probe just really returned the goods. And this is a picture taken from 8 kilometers altitude. And you could clearly see something that looks like a shoreline and a drainage pattern. We know now that this area here is about 100 meters elevation above the dark area, and this drainage pattern, you could follow it, and it actually moves away from the shore here, collects down in this area here. Here's one that comes down here. It was just shocking to see this. I mean, it was like being in one universe one moment and in another universe the next, to know that we were looking at the surface of a moon in the outer solar system, and it had undeniable evidence for flowing liquids on it. Again, this is taken at 8 kilometers altitude. If you were to fly in a jet from San Francisco to New York, you would fly at an altitude of something like 11 kilometers. So this is not unlike the view that you would have outside Titanian Airlines as you flew across the surface of Titan. But then, of course, the moment of truth came when the probe finally landed on the surface and returned this picture. And so this really was landfall in the outer solar system, a historic moment. I hope you can see it looks a little washed out, but here is the horizon in the distance, taken by 3 cameras looking 1, 2, and 3, so they're all put together in a mosaic. And here you could see these cobbles. I think we all still think they're made out of water ice. They're about this big, and they seem to be very well sorted. That is, the same size all throughout. The probe obviously landed in an unconsolidated ground that was wet with liquid methane. Okay, so it landed in the equivalent of a mud flat, and very likely, because it's a low-lying region, very likely formed by the material, the organic sludge that had been over, who knows, hundreds of millions of years, washed off the mountain peaks and into basins like where the probe landed. A very exciting moment. It was like, this part of the mission was like a Jules Verne adventure come true. And it was just a remarkable moment. But there were no lakes of liquid hydrocarbons. This happened in January of 2005. We didn't see anything that looked like a lake in the equatorial regions, and it wasn't until we finally got Cassini into an inclined orbit and could look down at the poles that we started to see things that looked like they were bodies of a liquid. And then finally, of course, the radar instrument was pressed into service, and it has returned some remarkable things. Here is a body of methane, some ethane also in the north. It's called Ligeia Mare. You could clearly see river channels leading down into it. It looks here like the coast of Maine. Okay, just really beautiful. This is just one. Eventually, they had long swaths across the polar region. Here's one. This is false. All of this is false color. These are radar instruments. These bodies of hydrocarbons. And then when they got enough data collected over the last 11 years, this is what the northern part of the body of Titan looks like. This is latitude, I think, about 60 degrees, but you could see this vast system of lakes. Actually, this region here is really all connected, and if you scaled up Titan to the size of the Earth, this region here would be the size of the Mediterranean. So there's a lot of fluid, a lot of liquid hydrocarbon on Titan, that all of it has just gone to the poles, most of it to the North Poles. We're not quite sure yet what has made the liquids go to the poles. First guess, of course, is temperature. It has been for all southern summer, it's been colder in the north, and so it stands to reason that the fluids would go there. We did get to see also this beautiful specular reflection glinting off one of the seas in the north, taken by one of the other instruments that can see down to the surface. So we have a lot of questions about why Titan looks the way it does. So lots of things are not clear to us. But one thing is very clear, and that is that after decades of speculation about what might lie on the surface of this intriguing moon, we have found an utterly fantastic place. And I mean that in the literal sense of that word. It's a land of fantasy. It's the only place in the solar system where we have liquid organics ponded on the surface and lacing its atmosphere. Liquid organics that we think are native to Titan. It's a place that is both exotic and alien and yet familiar in its landforms and the processes that are ongoing on its surface. And it's a place that in all the solar system, in its complexity, its geological complexity, and its geographical diversity is rivaled only by the Earth itself. So Titan remains a target of our affections, if you will. We are going to devote more flybys in the next 2 years on Cassini to Titan. And you'll be hearing a lot more about it. But of course, I've saved the best for last, and that is the tiny moon Enceladus, an icy moon of Saturn. And as far as I'm concerned, the most profound thing we have found on Cassini has been what we found capping the south pole of this moon. Here just gives you a feel for how big it is. It's no bigger across than England. This, by the way, is not meant to be a threat. And this in fact, is a picture taken by Cassini, but if we get 10 times closer, this is what we saw. It looks almost nothing like any of the other moons. It has obviously had a very complicated geological history, generations of fracturing, crisscrossing fractures, deep chasms, very few craters, lots of tectonics that produce features like this, mountain folds and ridges, and so on. So very different, very unusual. And the mother lode of discoveries that we have made on Enceladus is at the South Pole. And this is what we see there. The exact South Pole, I hope I'm not going to trip here. The exact South Pole, I think, is about there. This region is characterized by, is circumscribed by a belt of mountains and folds and ridges and valleys that are kind of wiggly also. And it is characterized by these 4 fractures. We call them the tiger stripes, because from a distance they looked like the stripes on the back of a tiger. This is a very, very extreme false color picture. To your eye, Enceladus would look as white as the driven snow. It's the whitest, brightest object in our solar system, and you'll see why in a minute. These fractures are about 120 kilometers long. They're about 35 kilometers apart. Nary a crater, very young region. And the instrument on Cassini that can measure thermal radiation found that there was an enormous amount of heat coming from this region, and it's the South Pole. That would be like saying the Antarctic is warmer than the Earth. It was very puzzling. And then when we were in the position to put Cassini, when we put Cassini in a position to look over the pole in the direction of the sun, which is a geometry which highlights the presence of small particles, this is what we saw. Okay, dozens of these fine jets that shoot hundreds of kilometers into the space above the South Pole of Enceladus, which is right about there. And if you take a picture like this and you color code the different levels of grays to make them easier to see, this is what you see. The jets feed a plume of material that extends, some parts of it extend thousands of kilometers into the space away from Enceladus. And in fact, those particles, in our pictures, that's what you're seeing is very tiny ice particles. Those particles escape Enceladus and go into orbit around Saturn and form the E-rings. So we had found what was forming the E-ring, which had been discovered around Saturn in the 1960s. Now, Cassini has flown through this plume several times, actually several. Now it's something like 19 times. We have our 20th flyby next week, and it has sampled the plume. There's an instrument on board, there's 2 in fact, that can pick up material and tell what its composition is. And we have found that the particles coming from the South Pole of Enceladus are salty. They're water, but they're salty. They have a salinity comparable to the Earth's oceans. And those particles are accompanied by vapor. And that vapor is water vapor, but it's laced with simple organic compounds. And it has a bit of ammonia, and it has carbon dioxide. These are all the compounds that are believed to be important in the origin and the maintenance of life. So very exciting. Images like this and like these. This is our highest resolution image we ever took, about 55 meters per dot that you see. That's the one I just showed you. Here's another one taken later on in the year when the shadow of Enceladus is creeping up the jets because the South Pole is going into darkness. Images like these, images even like this. This is looking in the direction of Saturn. Actually, remember, Enceladus keeps the same face towards Saturn. But you could see here the feet of these various geysers. All these images have allowed us to survey, and there's many more, survey the south polar terrain and determine just exactly the locations of all those jets. And in fact, their 3-dimensional configuration. This is work actually that I'm now talking to you now about research that I've done with my research group. And from all this information, we've been able to make a movie of showing you where all these jets are. And this is what their configuration looks like. They're not exactly vertically coming out. Some of them are tilted. Some fractures are more populated than others, but this is what we've seen. And we've also been able to show, which has been really exciting, that where there are jets, there is the greatest heat. In fact, the heat is coming from the fractures, most of it, and the heat seems to be the thermal signature of the geysering process, so all of the jetting process. So all this information put together and the data gathered from other Cassini instruments over the last 11 years has allowed us to deduce that these jets are in fact geysers, and they erupt through fractures in the ice shell from an ocean of salty liquid water that is some 25 kilometers below the surface. So we are now confident, after all this time, that Enceladus presents to us what in our business we call an extraterrestrial habitable zone. Or in other words, it is not out of the question that we have prebiotic chemistry and perhaps even life, perhaps, residing within this moon. And in that case, it's not completely crazy that it is snowing microbes at the south pole of Enceladus. Now, Cassini is unfortunately not equipped to answer the question as to whether or not we have extraterrestrial life on this moon. That will have to wait for a follow-on mission, and there's a group of us that are eager to do that, and we're planning that as I speak. But I don't think I need to, or I could stress this too strongly, that should we ever make such a discovery, if we ever anywhere find that there has been a second independent genesis in our solar system, then I think at that point the spell is broken. The existence theorem has been proven, and we could safely infer from that that life is commonplace, that it is not a bug, but a feature of the universe in which we live, and that it had occurred a staggering number of times throughout the 13.7 billion years of the history of the cosmos. And I think that that might be the kind of discovery that could change a great many things. And so, because of all the thrills and the excitement that this little moon has afforded us, I'm holding on personally to one very fanciful notion, and that is that someday in the far, far future, our descendants just might voyage back to the Saturn system to visit the Enceladus Interplanetary Geyser Park in a spaceship not unlike the Starship Enterprise. So for now, in the meantime, Cassini continues to orbit Saturn, and it continues to return one discovery after another, and brilliant, deep insights into how the Saturn system works and how our cosmic neighborhood came to be. And when it is all over in 2 years, I am certain that it will go down as one of the most, if not the most, scientifically productive missions that NASA has ever flown. I mean, how could it be any different? Spending what will that, by that time, be 14 years in the most beautiful, the most phenomenologically rich planetary system that we have in our solar system. But more than that, the story of Cassini, like the story of all our other interplanetary explorations over the last half century, has been a story about longing, a longing to know ourselves, a longing to understand us. And despite all that I've shown you this evening, despite all that we have been witness to over the last 11 years, there is an image that speaks of this longing so much better than words ever could, and it has a bit of a backstory, and so I want to share that with you now. Back in the 1980s, I had the pleasure of hitching a ride on what was the best adventure ever, and that was the Voyager mission to the outer solar system. And during that time, I had the privilege of coming to know someone you all know, Carl Sagan. And I had the honor of working with him and others in the planning and execution of what is now called the famous pale blue dot picture of Earth, taken in 1990 by Voyager 1 out beyond the orbit of Neptune. And it's not well known, but in the proposal that Carl wrote to the Voyager project, urging them to take such a picture because they didn't want to take it, and he tried for many years. I had tried also, and we ended up joining forces. Carl wrote that really the idea was to take a picture of the Earth, and I quote, "awash in a sea of stars." Well, if you remember the actual pale blue dot picture, it wasn't exactly what we had envisioned. There were no stars, and the Earth was unfortunately caught sitting on a beam of sunlight that had been scattered in the optics of the camera. Of course, none of this really mattered, because it wasn't the picture, but what Carl had to say about the picture, and the way that he romanced it, and the way that he turned this little picture into an allegory on the human condition that has ever since made the phrase pale blue dot synonymous with an inspirational call to planetary brotherhood and protection of the environment. Well, ever since the beginning of the Cassini mission and my tenure as the leader of the imaging team, I have had it in my mind to do this picture over again, only make it better. And it occurred to me somewhere along the way, somewhere in the planning of it, how great it would be if instead of taking a picture of Earth from Saturn and then announcing to the world, like had been done many times since the original pale blue dot picture, right? Lots of missions have taken their own pale blue dot picture, and then 2 days later, 2 weeks later, they release it to the public and they say, "Hey, world, while you weren't looking, guess what we did?" Okay, it occurred to me, why don't we tell people ahead of time? At such and such a date, such and such a time, your picture is going to be taken from 1 billion miles away, from an orbit around Saturn. And why don't we invite them at the appropriate time to go out, contemplate the utter isolation of our planet in the blackness of space, appreciate the rarity that it is among the planets in orbit around our sun, and marvel at their own existence and the existence of life on our planet. And so it happened. On July 19, 2013, 2 years ago, the Cassini cameras were turned to look at Saturn while it eclipsed the sun, to take another pale blue dot picture of the Earth, and we sent out the word. As the time is approaching for this picture, straighten up, comb your hair, go out, look up, think about all of us together on this pale blue dot. Think about this magnificent achievement that this interplanetary salute between robot and maker represents, and smile. And people responded just exactly the way I had hoped. Many comments came in from people all over the world describing a feeling of unity with their fellow humans, and here are just a few that I want to read to you because they're precious. We've got a lot of them, but these are ones that I culled out. So this is from Sam. Phoebe, age 10, and I got the telescope out on the patio. Under a beautiful, clear, southern British sky, we gazed upon Saturn, reveling in the fact that a spacecraft was looking back at us. She asked a lot of questions about Saturn, and at the appointed time, I raised a glass of fine red wine, she a glass of fizzy pop. We said, cheers to Saturn, to Cassini, to each other, and then we smiled and laughed and waved and cheered and took photos of ourselves, both beaming. It was perfect. This is Chris. I was in Reykjavik, Iceland. We went down to the waterfront and threw a wave in a general upward direction. This is Tess. I don't exactly know where she was, but anyway. At the appropriate time, I left the table at a restaurant and went to the parking lot. I turned my face to the sky and I spent a few minutes watching and listening to what life on Earth was like, right there, right at that moment. What a feeling of connection and oneness with the miracle that is life on Earth. This experience was beyond meaningful. It was transcendent. What a beautiful thing. Thank you. This is Jolyn. I've been entranced by this project ever since I heard about it and was determined to join in the celebration. However, I never anticipated how emotional I would feel. I stood on the edge of Lake Ontario in upstate New York with my son and his girlfriend. I had forgotten to bring my cell phone with its app that shows the location of Saturn, so in the end, we just spun in circles waving at the sky. They must have looked like a bunch of crazy people. The thought that a camera was taking pictures from so very far away was just incredible. We may not be unique, we may be transient, we may be only flying along on a dust mote, but darn it, for those 15 minutes, we were there, we were aware, and we smiled. And so it was a tremendous success as far as I was concerned. And here now, of course, is the mosaic that was taken as these people and many, many more were thinking about their cosmic place and smiling. It's a picture that I call the day the Earth smiled. You have seen it on, I bet, no doubt. This is Saturn eclipsing the sun as we had planned because we couldn't look directly into the sun or we would have ruined the cameras. Here is Enceladus, and this is the ring that is created by the spray coming off Enceladus. This is the moon Tethys, a moon of Saturn, and you could see the rings, the main rings of Saturn, very luminous, like they're glowing because they're being diffusely lit from behind. And if you look over the shoulder of Saturn, in the distance, 1 billion miles away, is our planet Earth, which, if you look in the narrow angle camera, which we did, you see, for the first time from the outer solar system, the Earth and the moon. Yes. So as evidenced by your reaction, which is not unusual, there is something incredibly powerful that we feel when we see sight of our own fragile, blue, ocean-covered little world as it would be seen by others in the skies of other worlds. And I think that it is that startling and uncorrupted recognition of ourselves as we are, where we are, that never fails to move us. And it moves me to think about evolution. In fact, for me, this is the picture where the Italian astronomer Galileo and the English biologist Charles Darwin come face to face. Because it is a picture that was ultimately made possible by Galileo's first experiments with gravitation over 400 years ago, and it is a picture that shouts evolution. I look at this picture and I see our distant ancestors stepping down from the trees and walking upright for the first time onto the African savannas and pausing to look back at the forests from which they came. And I look at this picture and I see a species that is positively relentless in its pursuit of knowledge and brave and ardent in its longing to grasp the meaning and the significance of its own existence. And finally, I can't help but look at this picture and see the very, very best that humanity has to offer. If you're paying any attention at all, you know we are the cruel and troubled and warlike inhabitants of one tiny little dot of a planet, and we are reminded of this day in and day out all over the globe, wherever we look. But in those moments of great existential despair, and I have them and I'm sure you have them too, it would be worthwhile to remind ourselves that we are also the dreamers and thinkers and explorers who took this picture. One world clear across interplanetary space to another. And to be so small and reach so far is, in the end, what makes us the extraordinary citizens of planet Earth. And it's that proud perspective of ourselves that is, I think, Cassini's greatest legacy, and the legacy that it and all its other interplanetary brethren will leave behind. And I say, let's revel in it, because we deserve it. Thank you.
Okay. You mentioned that the mission will end in a couple of years. I was wondering, first of all, why does it end? Out of fuel, out of money, out of power? And where will it end? Do you just put it in a parking orbit, or what happens to the spacecraft?
Okay, so first of all good things must end. And we couldn't go on forever spending NASA's money, because there are other missions that are waiting to start, and they're good missions and they have to happen. So we made a decision on the Cassini project years ago that we would do the following. We arrived at the height of southern summer, and we thought it would be best if we got to at least the height of northern summer, because that means between the two hemispheres, we would have seen the full seasonal cycle on Saturn. We don't have to wait there 28 years to do it. 14 years is adequate. We see the southern hemisphere go from summer to winter. We see the winter hemisphere go from winter to summer. The height of northern summer is going to be September 2017 or thereabouts. Since we had planned that as a termination point, that determined how much we utilized the spacecraft, the rate at which we utilized the spacecraft resources in between. So anyway, that was the decision, and I forget, how are we going to do it? Well, we're going to send the spacecraft, if it doesn't do it on its own, by running into a ring particle or becoming unstable on its own, we're going to send it into the atmosphere of Saturn. And people say, why don't you do something else? Why don't you leave it there? You could use it for A, B, and C. But since we have two bodies in the Saturn system that are of great astrobiological interest, Titan, because it's the only place we know of that's got organics on the surface, and Enceladus, because it's the best place in the solar system to go searching for life because it's easy to sample. We don't want to mess it up by accidentally, even if it's a remote chance, of seeding it with organisms that could still be on the spacecraft. Seems extreme, but it's just, it's not a big deal to do. And so that's what's going to happen to Cassini. Okay, so go over here. Yes, you?
So you showed the rather three-dimensional orbit pattern around Saturn, and I wasn't sure if that was pre-set up before arrival. So I wondered if it's the first, kind of what made you choose that in particular, and if it's the second, how do you make the choices to adapt it?
That has to be planned in advance because it's very, very complicated work. And it goes in steps. First the scientists say, we really need to visit Enceladus, let's say, so many times. We want to visit Dione so many times. We want to have so many views of the rings from this kind of distribution of angles. We need to look at the planet from this solar illumination angles, and there's all these geometrical requirements that we place on the mission designers, and the mission designers go off and work to figure out what kind of tour they can design that meets the most of our objectives. And so the 4-year tour was planned, all of it, the nominal 4-year tour, because remember, Cassini's nominal mission ended in 2008. that was planned years in advance. And not only was the trajectory planned, but the scientists get into the act because we have to plan every minute of those 4 years. Every minute of those 4 years, we argue over them, and we say, well, we want them. No, I want them. No, they want them. And, you know, Titan is more important. No, Enceladus is more important. And that goes on and on and on and on. So that's the part of the Cassini mission I will not miss. So it's arduous. It's a lot of work. And then when we were given, you know, the go-ahead to do extended missions, those too were planned very much in advance. Now, that doesn't mean we don't take advantage of new discoveries and tweak things so that, you know, classic example was we discovered the plumes erupting of Enceladus early, very early, January, February, in our images. And other instruments also found material coming off the moon. And what was done with all that information was to alter an upcoming flyby that was going to happen in July, so some 5 to 6 months later, and we lowered the approach, the closest approach point, so we could get a better look. You couldn't really change the tour too much at that point, but you could get closer or farther away from something, and that's what we chose to do. So this, by the way, has been the core, one of the main hallmarks of our success is the fact that we are there, we're in residence at Saturn. We have the leisure to take observations, and then if we find something exciting, go back and look at it again and again if we like, and that's what we've done. So over here.
Could you say a little bit about the types of image processing that you need to do for a mission like this?
The type of image processing? It depends for what purpose. I mean, if you're talking about just making beautiful images, we have to work with calibrated images, so we know how to calibrate. We spent a lot of effort to learn how the instrument responds and how we take the number that comes out of the camera, so to speak. We just call it a data number. It could be 4. It could be, you know, 670. It could be some number. We know how to convert that into a brightness. It tells us how much light is coming from that pixel. And that's calibration. And so we know that, and then we do that in several filters to make a color picture. If you're making a natural color, we choose blue, green, and red. We composite them together. We know pretty much how the balance goes between those three, although we don't really know it to a really high degree of accuracy, so there's always some, you know, mushiness about just exactly what true color is. I could never promise you that something was exactly true color, but that's how you do it just to make a pretty picture. We've done other things like make sure, you know, in 3 pictures you have moons that are moving through, and rather than have a picture that's got, let's say, you know, Enceladus looking blue, green, red, we deliberately, you know, composite them. So we cheat a little bit, and we, you know, take the 3 images, put them on top of one another, and put it in the final image. But that's for just public release. I mean, there's lots of things we do to extract scientific information. I could bore you with it for hours. I mean, you know, so. Okay, over here.
Speaking of beautiful images, you had a picture of the ring particles.
That was a artist's conception.
How close were you able to observe the actual appearance of ring particles?
Oh, you'd have to be really, really close to do so, to see them with a camera that had our kind of focal length. It's not possible. We couldn't get that close to the ring. So we never on Cassini saw a ring particle. We see them all acting together en masse, almost like a fluid. Okay? Yeah, over here.
I'd like to better understand the mechanics of the formation of things like rings and moons and planets and asteroid belts. You were saying about the Saturn rings that the violent collisions had died out, so they're not the kind of collisions that apparently still occur in the asteroid belt. And then the formation of the planets was via an accretion process that apparently is also not happening in the rings. What are the differences in mechanics that make those differences?
I don't think there's much difference in mechanics. It's just, you know, you start out with a cloud, a rotating cloud, and then it's basic physics. You know, all natural materials, when they collide, they lose energy. They're not perfectly elastic. So you lose energy, but you retain, you conserve angular momentum, and that gives you a situation where you have a cloud of material. As long as the particles are colliding with one another, they lose energy, but they retain angular momentum. They end up flattening out into a disk and spreading out. Okay, and if there are still violent collisions going on in there, just think about it. Those violent collisions will destroy the particles, and you'll end up with a system where what's ever left is going predominantly or mostly in circular orbits. The kind of eccentricities that we do see in Saturn's rings, and we do see, very, very small eccentricities, are usually excited by moons. Okay, and in the asteroid belts you get in the asteroid belt you get asteroids whose eccentricities are excited by the other planets. You do get collisions because it's very rarely do you get collisions, but you can get collisions because it's not nearly as densely populated as the rings. So, you know, it depends how frequent the collisions are that matters in this.
Well, it depends maybe also on whether the moons are sort of shepherding the material like in the rings, and the planets are shepherding the asteroids, and there's a difference in the mechanics of the interaction?
No, I don't think so. It's just that the frequency of collisions is different because the density of particles is different. You know, it's why the B ring looks very much different than the D ring or the C ring, because the collective effects, particles to particles, work differently. So I better give somebody else a chance, or we'll run out of time. Yes?
Carolyn, the pale blue dot that you took was marvelous, but when it zoomed in to see the Earth and the Moon, I was totally astounded. My question is quite simple. Are these images available on the web?
Oh, yeah.
Can you tell me the web address?
Okay. So our website is cyclops.org, CICLOPS.org. It's an acronym. I learned how to do acronyms from JPL. Cassini Imaging Central Laboratory for Operations.
It's in the handout.
Hey.
It's in our handout.
Well, and I can also do this. Okay. So I have a search thing. You can search for, let's see, what did we call it? Search for Day the Earth Smiled, and you ought to get to the web pages where we have the preview. And then it took us months to do that picture. I mean, it took us, talk about image processing, you have no idea how much time it took us to do that picture.
It's beautiful.
Yeah, it is. It's, I see places where it needs to be improved, but I won't tell you where they are. Okay, yes.
Hi, I just wanted to thank you for your talk, both for the information and the inspiration.
Okay.
And yeah, it was worth the wait.
Oh, good. 16 years or whatever it's been.
Yeah. So my question is in regards to timescale. So we have these snapshots taken over the last 10, 12 years of, say, the rings or the plumes on Enceladus or the lakes on Titan. So what can we infer about how long these things have been around and how long they might last?
Well, you just threw a whole lot of things together in one, in one thing. So, how long the geysers on Enceladus might last is a big question that we're trying to wrestle with, and that gets into just exactly how it got into the configuration it's in now. It's in a resonance with Dione that is in fact the source of all its heat, we think. Effectively, it's the source of all its heat. So if there was a way for it to pop out of resonance with Dione, then eventually the thing would probably cool off, but we don't expect that's going to happen. The hydrocarbon lakes on Titan, I couldn't answer. I know they don't even know how they got there. They can't even get the budgets to work out how much methane there is in the atmosphere, how much there is on the surface. These are, it's called exploration, and we're trying to figure all this out now. So I can't give you any hard and fast answers. Sorry, but I can't. All right. Yes, over there.
Hi. In the artist's conceptions of the rings, it showed like each of them as sort of a large boulders of ice, sort of separate from each other. But when you show the picture of the edge of the B ring with the large mountains, ranges, and stuff like that, it looked like a solid ring. Is that true or not?
Okay, so first, that artist's conception, I always mean to update it, and I don't know, I'm sure someone's done a better job. That's not really what the size distribution looks like. I just want to take this opportunity to correct this.
Okay.
There's fewer big particles than small particles, but they are all in a plane, pretty much all in a plane. And whether or not it looks in the artist's depiction, whether or not it looks like it's solid or really dense or not, depends on whether or not the artist was thinking that he or she was painting the middle of the B ring where the particles are very densely packed, or so much so that they almost act like grain in a grain silo, or they're painting the C ring where the particles are very underdense. And as I said before, in our pictures, we are so far away that you can't resolve individual particles. So it will always look like a faint sheet of something.
But there's no part of the ring that's completely connected all the way around.
All the rings are completely connected all the way around.
But like solidly connected, not.
There's no solid, solid like a, like what? Like a washer? Nothing like that.
So the mountains on the edge of the B ring are not like connected in
They're
any
not
way.
mountains in the sense of being a contiguous mass. They
Right.
are, think of them as piles of rubble. Rubble mountains are made of rubble. Mountainous piles of rubble. That's
Right.
it. Okay?
Okay, thank
So
you.
you could almost play a game of, I'm sure some daring guy would want to do this, get in his shuttlecraft and try to
Could you
poke
land
through
on it?
without getting hit.
Is there enough gravity to actually land on any of those spots there, or is it
Excuse me, enough gravity to land on
to
any one?
land on the ring, on any part of the ring that's?
Well, let's see. So the largest ring particles are, they're like, 10 meters across. If you had a small enough shuttlecraft, you might be able to do it if you deftly maneuvered it. But it's in a, it's in a debris field. It'd be a dangerous thing to do.
Okay.
You try it. Three more. Okay, over here.
Hello.
Hi.
Thank you very much for coming by. That's, for me, completely unusual to come to a community college, so that is awesome.
Okay.
So from a social science background, the fancy pictures and the way you speak really resonates with me. That's awesome. What I ask myself, especially looking through the room, especially looking at the hair color of the majority, I ask myself, how can we, no offense, sorry. How can we take this incredible inspiration on to the next generation? How do you convince the next generation to do even better than you guys did, because you did a phenomenal job, but how do you carry that torch, so to say? I know that this gentleman over here does a phenomenal job in his astronomy class that I'm taking, and you're doing a phenomenal job right here, but there are only so many of us that are sitting here that are below, I'm not going to just say a number, but you know what I mean.
Well, okay, so first the younger generation is, believe me, there's a lot of younger generation people behind me getting ready to do some amazing things with the missions that are going to happen next. So, it's the younger crowd, actually, mostly at JPL, that's doing the Mars missions. Europa is going to get started if it doesn't encounter any, severe setbacks. It's about to happen. There's going to be young people working on that. So I think there'll always be people who want to be on these missions because they're, like I said, it's a high, and it's like, after a while you become a junkie. and you can't like not do it. But why there aren't younger people here, I don't know. They're probably all at home, you know, on their cell phones, waiting for this to get to the web because they don't want to come out here, right? Don't you think? You're going to put it on YouTube, and then 750,000, you said, are going to see it.
Actually, maybe just to rephrase the question, not for the scientists, because, I mean, the scientists, of course, they have an internal curiosity to explore and investigate.
You mean, how do you get it to the layperson?
Basically, yeah.
You know, we try. That's all I can say. I don't know. You know, you're younger than I am. Why don't you tell me?
We can talk.
What are we doing wrong?
You're not doing anything wrong by speaking like this, so that's pretty awesome. Now the question is, how do you get it to more people, right? The YouTube is definitely a good start.
Yeah, but I think this is a homework assignment. You go find out what we can do,
But-
and let him know, and then you tell me, okay? All right.
But thank you very much.
Okay, sorry, we got to move on. Yeah.
I think in answer to him, hiring image scientists like yourself and producing the images that you did are just so aesthetically pleasing and captivating. That's a huge boon to making people enthusiastic about this.
Okay, I can only take part credit here, you know, because Saturn happens to be the most photogenic body in all the solar system. So, I mean, it's hard to take a bad picture of Saturn. But anyway, thank you.
Yeah.
Well, I put a lot of effort into it to make it, you know, to just go that extra step.
Yeah, lucky assignment to be the image specialist on this mission.
Yeah.
Good for
okay.
you.
Well, I've said for the last 25 years I've got the best job in the inner solar system. So.
I did have a question about the temperature. It's so damn cold out there, and I'm wondering, for 14 years Cassini's been performing and doing things.
Well, it has
fairly actively. I'm wondering, is the cold a hindrance or a huge challenge, or is it actually like a preservative that keeps things in order when they're...
The thermal part of spacecraft design is, as far as I could tell, I'm not a spacecraft engineer, but I've been around them for a long time. That's the most challenging part. Thermal gradients just screw everything up. So you want to reduce thermal gradients. I don't think it's so much the temperature, but it's gradients. And, you know, when you're in space and there's no atmosphere, so that the energy is not conducted to you. Like right now, the atmosphere is conducting. It's touching me. I'm feeling the warmth of the atmosphere and not the vacuum of space. In space, there is none. That's the definition of it. So you have anything in space. The sun, let's put it at the surface of, let's put it in the orbit around Venus. The sunlight shining on it, it's very, very, very hot. But on the other side of it, where there's no sun, it's incredibly cold. Same thing on the moon. You know, when the astronauts were in shadow, it was incredibly cold. When they were in the sun, it was incredibly hot. I mean, both extremes. If they had no suit, they wouldn't have been able to live in either one. So that's because there's no conduction. Everything is radiative out there. So, I just happen to know that's a challenge. And they do things like we did this in our cameras. A thermal gradient across from the front to the back of the camera was a terrible thing because then it screws up. It's a long focal length camera. I mean, it's folded, but still. You get distortion because of that thermal gradient. So we have heaters in the cameras that, you know, reduce the gradient or try to keep it stable. So it is a challenge. That's the short answer. It's a challenge. Okay, over here.
Yes, looking forward, could you please briefly characterize your expedition to Enceladus?
My expectations for Enceladus? Okay, so we have 3 flybys, close flybys coming up, October 14, 28, and December 19. And these are the last of the mission where we're going to be flying really close. And in some of those flybys, the instrument that measures thermal radiation will have the opportunity now, because the sunlight is gone. We're in late autumn, approaching winter at the South Pole. there's no sunlight falling on the South Pole, so any radiation that that instrument sees has got to be coming internally from the moon. And that has been a problem with the interpretation of the thermal data taken when the South Pole was in sunlight. It was a little bit hard to figure out what's internal and what's external. But now the external is off, the lights are out, and so we're going to really look to see is there any regional heat coming from that whole South Polar cap, that whole South Polar region, which, by the way, if you scaled up Enceladus to the size of the Earth, that's like Tierra del Fuego, the latitude of Tierra del Fuego, and everything south. Okay, so that's one thing we're going to be doing, where they're also going to be trying to, at high resolution, see if they can look at one of our jets. So, because we want to, you know, at high resolution, look to see how the jet and the thermal radiation work together. What else is going to happen? Oh, and then, of course, the instruments that can scoop up material and measure composition, in particular the vapor, which, by the way, just as a little historical footnote, they were designed to work at Titan because no one, even though we thought there might be stuff coming off Enceladus, no one really designed instruments for that possibility because that would have been just too much. So they take this instrument that's designed to work at Titan and, you know, found a way to make it work at Enceladus. They are going to fly through the plume. We're flying low, rather. The spacecraft's going to fly through the plume. They're going to scoop up material. And they're using a different mode on their instrument specifically to see if they could measure molecular hydrogen. Why is molecular hydrogen interesting? Because they're the best analogs that we can think of now. It's not to say years from now we won't find more, we won't think of more, but right now, the best ecologies on the Earth, which are the best analogs for what we think might be going on Enceladus, involve hydrogen. There are organisms miles below the surface of the Earth. They live in the absence of sunlight. They live in the absence of anything created at the surface, nothing having to do with photosynthesis. These organisms live by eating molecular hydrogen and carbon dioxide, or in another place on the Earth, molecular hydrogen and sulfur sulfate, SO4. And they're happy where they are. So we just want to know, is there molecular hydrogen in the plume? And that's what we're going to be asking.
Yeah, those are cold seeps, with methane cold seep you're referring to in the ocean.
These are not in the ocean. These are underneath. One is in volcanic strata. I think under the, I think part of the Columbian basalts, I think, and another is in, I think, South Africa somewhere. Okay, what, one more? I think we're done. We're done. Okay, thank you everybody for coming out.